4G is much faster than 3G, and this has revolutionized the field of telecommunication by bringing the wireless experience to a new level altogether. 4G systems support interactive multimedia, voice, video, wireless internet and other broadband services. Technologically, 4G is very different compared to 3G. Unlike the predecessor networks of 4G, i.e. 2G and 3G, which consisted of well-defined cellular network components, 4G networks are expected to consist of a collection of wireless networks. These would include the personal area networks using, for example, Bluetooth, the local area networks using WLAN, the satellite-based mobile networks, and enhanced 3G cellular networks, besides others. The vision of 4G mobile networks is to bind these different wireless technologies together in such a manner so as to provision broadband access and global roaming using the most appropriate of these technologies. The 4G mobile networks are being developed with two main objectives. One of these objectives is to overcome the shortcomings and limitations of 3G, prime amongst which is the issue of available bandwidth. The 3G specifications have been defined to offer maximum bandwidths of 2 Mbps. However, this figure of 2 Mbps can be highly misleading. While 2 Mbps is the maximum achievable bandwidth in 3G, in practical scenarios, the bandwidth available to users will be quite less than 2 Mbps. It is expected that in most realistic scenarios, users of 3G networks will be able to receive bandwidths of around 384 kilobytes per second. Bandwidths near the 2 Mbps value will only be achieved in restricted cases, involving low mobility and in picocells. Even though the bandwidths offered by 3G networks is an order of magnitude better than their 2G counterparts, it is still not sufficient to support all types of multimedia communication. 4G mobile networks are being envisioned to offer higher bandwidths, up to a value of 100 Mbps. Besides the bandwidth limitation of 3G, other shortcomings of 3G are related to the issue of global roaming and network scalability. 3G technologies were originally proposed to provide global roaming. Global roaming implies that a subscriber roaming across the globe would always remain connected. The original goal as envisaged by ITU was to have a single radio interface that provided global roaming. However, in actuality, a set of 5 standards for the radio interface were adopted for third-generation, 3G, networks, since it was felt that having multiple standards fostered competition and also catered to the migration of the installed base of second-generation networks. Hence, current implementations of 3G have failed to achieve the requirement of global roaming. Therefore, global roaming has been added as one of the requirements from the future 4G networks. Further, 3G specifications define 3 different core network CN domains, where each domain provides a different set of services. The CS domain is defined to provide circuit-switched services and, the PS domain the packet-switched services, and the IMS domain, the IP multimedia services. Many researchers feel that the present 3G network architecture is not scalable and is not suitable for the next generation mobile networks. Hence, for the 4G networks, enhanced network architecture is being proposed which is expected to be entirely a packet-switched network. The second main objective behind 4G developments is to make good use of the achievements in the area of wireless technology. The sluggish pace of 3G deployments has provided an opportunity for other wireless technologies to capture a sizable portion of the market. Prominent amongst these other wireless technologies is the wireless LAN, WLAN, and Bluetooth. As the name suggests, WLAN provides a wireless solution to networking in LANs, while Bluetooth is used to communicate between smart devices in a personal area network, PAN. Satellite-based mobile networks, e.g. Thuraya, are also popular, and these provide an efficient means of offering wireless services in sparsely populated areas. Thus, the next generation of mobile networks would have to accommodate such other prominent wireless networks as well. The 4G network architecture is expected to consist of a collection of such wireless networks, the 3G cellular network being just one of these. 4G is the fourth generation of broadband cellular network technology, succeeding 3G and preceding 5G. A 4G system must provide capabilities defined by ITU in IMT Advanced. Potential and current applications include amended mobile web access, IP telephony, gaming services, high-definition mobile TV, video conferencing, and 3D television. However, in December 2010, the ITU expanded its definition of 4G to include long-term evolution, LTE, worldwide interoperability for microwave access, WiMAX, and evolved high-speed packet access, HSPA+. The first release WiMAX standard was commercially deployed in South Korea in 2006 and has since been deployed in most parts of the world. The first release LTE standard was commercially deployed in Oslo, Norway, and Stockholm, Sweden in 2009, and has since been deployed throughout most parts of the world. However, it has been debated whether the first release versions should be considered 4G. The 4G wireless cellular standard was defined by the International Telecommunication Union, ITU, and specifies the key characteristics of the standard, including transmission technology and data speeds. Each generation of wireless cellular technology has introduced increased bandwidth speeds and network capacity. 4G has speeds of up to 115 bits/s download and 15 bits/s upload, whereas 3G had a peak speed of 7.2 bits/s download and 2 bits/s upload. As of 2021, 4G technology constitutes 58% of the worldwide mobile telecommunication technologies market. In November 2008, the International Telecommunication Union Radio Communications Sector, ITUR, specified a set of requirements for 4G standards, named the International Mobile Telecommunications Advanced, IMT Advanced, specification, setting peak speed requirements for 4G service at 100 megabits per second, mbit/s, equals 12.5 megabytes per second, for high mobility communication, such as from trains and cars, and 1 gigabit per second, bits/s, for low mobility communication, such as pedestrians and stationary users. Since the first release versions of mobile WiMAX and LTE support much less than 1 bit/s peak bit rate, they are not fully IMT Advanced compliant, but are often branded 4G by service providers. According to operators, a generation of the network refers to the deployment of a new non-backward compatible technology. On December 6, 2010, ITUR recognized that these two technologies, as well as other beyond 3G technologies that do not fulfill the IMT Advanced requirements, could nevertheless be considered 4G, provided they represent forerunners to IMT Advanced compliant versions and a substantial level of improvement in performance and capabilities with respect to the initial third-generation systems now deployed. Mobile WiMAX Release 2, also known as Wireless MAN Advanced or IEEE 802.16m, and LTE Advanced, LTEA, are IMT Advanced compliant backwards compatible versions of the above two systems, standardized during the spring 2011, and promising speeds in the order of 1 Gbps. Services were expected in 2013. As opposed to earlier generations, a 4G system does not support traditional circuit switch telephony service, but instead relies on all Internet Protocol, IP-based communications such as IP telephony. As seen below, the spread spectrum radio technology used in 3G systems is abandoned in all 4G candidate systems and replaced by OFDMA multi-carrier transmission and other frequency domain equalization, FDE, schemes, making it possible to transfer very high bit rates despite extensive multipath radio propagation, echoes. The peak bit rate is further improved by smart antenna arrays for multiple input multiple output, MIMO, communications. In the field of mobile communications, a generation generally refers to a change in the fundamental nature of the service, non-backwards compatible transmission technology, higher peak bit rates, new frequency bands, wider channel frequency bandwidth in Hertz, and higher capacity for many simultaneous data transfers, higher system spectral efficiency in bit/second/hertz/site. New mobile generations have appeared about every 10 years since the first move from 1981 analog, 1G, to digital, 2G, transmission in 1992. This was followed, in 2001, by 3G multimedia support, spread spectrum transmission and a minimum peak bit rate of 200 kbit/s, in 2011/2012 to be followed by real 4G, which refers to all IP packet switched networks giving mobile ultra broadband, gigabit speed, access. While the ITU has adopted recommendations for technologies that would be used for future global communications, they do not actually perform the standardization or development work themselves, instead relying on the work of other standard bodies such as IEEE, WiMAX Forum, and 3GPP. In the mid-1990s, the ITUR Standardization Organization released the IMT 2000 requirements as a framework for what standards should be considered 3G systems, requiring 2000 kbit/s peak bit rate. In 2008, ITUR specified the IMT Advanced, International Mobile Telecommunications Advanced, requirements for 4G systems. The fastest 3G-based standard in the UMTS family is the HSPA Plus standard, which has been commercially available since 2009 and offers 21 bit/s downstream, 11 bit/s upstream, without MIMO, i.e. with only one antenna, and in 2011 accelerated up to 42 bit/s peak bit rate downstream using either DCHSPA+, simultaneous use of two 5 MHz UMTS carriers, or 2x2 MIMO. In theory, speeds up to 672 bit/s are possible, but have not been deployed yet. The fastest 3G-based standard in the CDMA 2000 family is the EVDU-Rev-B, which is available since 2010 and offers 15.67 bit/s downstream. 4G use IMT Advanced, International Mobile Telecommunications Advanced, as defined by ITUR. An IMT Advanced cellular system must fulfill the following requirements. Be based on an all-IP packet switched network. Have peak data rates of up to approximately 100 bit/s for high mobility such as mobile access and up to approximately 1 bit/s for low mobility such as nomadic/local wireless access. Be able to dynamically share and use the network resources to support more simultaneous users per cell. Use scalable channel bandwidths of 5 to 20 MHz, optionally up to 40 MHz. Have peak link spectral efficiency of 15 bit/s Hz in the downlink, and 6.75 bit/s Hz in the uplink, meaning that 1 bit/s in the downlink should be possible over less than 67 MHz bandwidth. System spectral efficiency is, in indoor cases, 3 bit/s Hz cell for downlink and 2.25 bit/s Hz cell for uplink. Smooth handovers across heterogeneous networks. In September 2009, the technology proposals were submitted to the International Telecommunication Union, ITU, as 4G candidates. Basically, all proposals are based on two technologies. LTE Advanced standardized by the 3GPP. 802.16m standardized by the IEEE. Implementations of mobile WiMAX and first release LTE were largely considered a stopgap solution that would offer a considerable boost until WiMAX 2, based on the 802.16m specification, and LTE Advanced was deployed. The latter's standard versions were ratified in spring 2011. The first set of 3GPP requirements on LTE Advanced was approved in June 2008. LTE Advanced was standardized in 2010 as part of Release 10 of the 3GPP specification. Some sources consider first release LTE and mobile WiMAX implementations as pre-4G or near 4G, as they do not fully comply with the planned requirements of 1 bit/s for stationary reception and 100 bit/s for mobile. Confusion has been caused by some mobile carriers who have launched products advertised as 4G but which according to some sources are pre-4G versions, commonly referred to as 3.9G, which do not follow the ITUR defined principles for 4G standards, but today can be called 4G according to ITUR. Vodafone Netherlands, for example, advertised LTE as 4G, while advertising LTE Advanced as their 4G Plus service. A common argument for branding 3.9G systems as new generation is that they use different frequency bands from 3G technologies, that they are based on a new radio interface paradigm, and that the standards are not backwards compatible with 3G, whilst some of the standards are forwards compatible with IMT 2000 compliant versions of the same standards. As of October 2010, ITUR Working Party 5D approved two industry-developed technologies, LTE Advanced and Wireless MIN Advanced, for inclusion in the ITU's International Mobile Telecommunications Advanced Program, IMT Advanced Program, which is focused on global communication systems that will be available several years from now. LTE Advanced, Long-Term Evolution Advanced, is a candidate for IMT Advanced Standard, formally submitted by the 3GPP organization to ITUT in the fall 2009, and expected to be released in 2013. The target of 3GPP LTE Advanced is to reach and surpass the ITU requirements. LTE Advanced is essentially an enhancement to LTE. It is not a new technology, but rather an improvement on the existing LTE network. This upgrade path makes it more cost-effective for vendors to offer LTE and then upgrade to LTE Advanced, which is similar to the upgrade from UCMA to HSPA. LTE and LTE Advanced will also make use of additional spectrums and multiplexing to allow it to achieve higher data speeds. Coordinated multipoint transmission will also allow more system capacity to help handle the enhanced data speeds. The IEEE 802.16m or Wireless MIN Advanced, WiMAX 2, evolution of 802.16e is under development, with the objective to fulfill the IMT Advanced criteria of 1 Gbps for stationary reception and 100 Mbit/s for mobile reception. The pre-4G 3GPP long-term evolution, LTE, technology is often branded 4G, LTE, but the first LTE release does not fully comply with the IMT Advanced requirements. LTE has a theoretical net bit rate capacity of up to 100 Mbit/s in the downlink and 50 Mbit/s in the uplink if a 20 MHz channel is used, and more if multiple input multiple output, MIMO, i.e. antenna arrays, are used. The physical radio interface was at an early stage named High-Speed OFDM Packet Access, SOPA, now named Evolved UMTS Terrestrial Radio Access, EUTRA. The first LTE USB dongles do not support any other radio interface. The world's first publicly available LTE service was opened in the two Scandinavian capitals, Stockholm, Ericsson and Nokia Siemens Network Systems, and Oslo, a Huawei system, on December 14, 2009, and branded 4G. The user terminals were manufactured by Samsung. As of November 2012, the 5 publicly available LTE services in the United States are provided by Metro PCS, Verizon Wireless, AT&T Mobility, US Cellular 19 Sprint, and T-Mobile US. T-Mobile Hungary launched a public beta test, called Friendly User Test, on October 7, 2011, and has offered commercial 4G LTE services since January 1, 2012. In South Korea, SK Telecom and LG U+ have enabled access to LTE service since July 1, 2011 for data devices, slated to go nationwide by 2012. KT Telecom closed its 2G service by March 2012 and completed nationwide LTE service in the same frequency around 1.8 GHz by June 2012. In the United Kingdom, LTE services were launched by EE in October 2012, by O2 and Vodafone in August 2013, and by 3 in December 2013. The mobile WiMAX, IEEE 802.16 times 10 to the power of -2005, Mobile Wireless Broadband Access, MWBA, standard, also known as WI-BRO in South Korea, is sometimes branded 4G, and offers peak data rates of 128 mbit/s downlink and 56 mbit/s uplink over 20 MHz wide channels. In June 2006, the world's first commercial mobile WiMAX service was opened by KT in Seoul, South Korea. Sprint has begun using mobile WiMAX, as of September 29, 2008, branding it as a 4G network even though the current version does not fulfill the IMT advanced requirements on 4G systems. In Russia, Belarus, and Nicaragua, WiMAX broadband internet access were offered by a Russian company Skartel, and was also branded 4G, YOTA. In the latest version of the standard, WiMAX 2.1, the standard has been updated to be not compatible with earlier WiMAX standard, and is instead interchangeable with LTE TDD system, effectively merging WiMAX standard with LTE. Just as long-term evolution, LTE, and WiMAX are being vigorously promoted in the global telecommunications industry, the former, LTE, is also the most powerful 4G mobile communications leading technology and has quickly occupied the Chinese market. TD-LTE, one of the two variants of the LTE air interface technologies, is not yet mature, but many domestic and international wireless carriers are, one after the other, turning to TD-LTE. IBM's data shows that 67% of the operators are considering LTE because this is the main source of their future market. The above news also confirms IBM's statement that while only 8% of the operators are considering the use of WiMAX, WiMAX can provide the fastest network transmission to its customers on the market and could challenge LTE. TD-LTE is not the first 4G wireless mobile broadband network data standard, but it is China's 4G standard that was amended and published by China's largest telecom operator, China Mobile. After a series of field trials, is expected to be released into the commercial phase in the next 2 years. Ulf Waldson, Ericsson's vice president, said, "The Chinese Ministry of Industry and China Mobile in the fourth quarter of this year will hold a large-scale field test. By then, Ericsson will help the hand." But viewing from the current development trend, whether the standard advocated by China Mobile will be widely recognized by the international market is still debatable. UMB, Ultra Mobile Broadband, was the brand name for a discontinued 4G project within the 3GPP2 standardization group to improve the CDMA 2000 mobile phone standard for next-generation applications and requirements. In November 2008, Qualcomm, UMB's lead sponsor, announced it was ending development of the technology, favoring LTE instead. The objective was to achieve data speeds over 275 mbit/s downstream and over 75 mbit/s upstream. At an early stage, the Flash OFDM system was expected to be further developed into a 4G standard. The iBurst system, or HCSDMA, High Capacity Spatial Division Multiple Access, was at an early stage considered to be a 4G predecessor. It was later further developed into the Mobile Broadband Wireless Access, MBWA, system, also known as IEEE 802.20. The following key features can be observed in all suggested 4G technologies. Physical layer transmission techniques are as follows. MIMO, to attain ultra-high spectral efficiency by means of spatial processing including multi-antenna and multi-user MIMO. Frequency domain equalization, for example multi-carrier modulation, OFDM, in the downlink or single carrier frequency domain equalization, SCFDE, in the uplink, to exploit the frequency selective channel property without complex equalization. Frequency domain statistical multiplexing, for example, OFDMA, or single carrier FDMA, SCFDMA, aka linearly precoded OFDMA, LP OFDMA, in the uplink, variable bit rate by assigning different subchannels to different users based on the channel conditions. Turbo principal error correcting codes, to minimize the required SNR at the reception side. Channel dependent scheduling, to use the time varying channel. Link adaptation. Adaptive modulation and error correcting codes. Mobile IP utilized for mobility. IP-based femtocells, home nodes connected to fixed internet broadband infrastructure. As opposed to earlier generations, 4G systems do not support circuit switch telephony. IEEE 802.20, UMB and OFDM standards lack soft handover support, also known as cooperative relaying. Recently, new access schemes like orthogonal FDMA, OFDMA, single carrier FDMA, SCFDMA, interleaved FDMA, and multi-carrier CDMA, MCCDMA, are gaining more importance for the next generation systems. These are based on efficient FFT algorithms and frequency domain equalization, resulting in a lower number of multiplications per second. They also make it possible to control the bandwidth and form the spectrum in a flexible way. However, they require advanced dynamic channel allocation and adaptive traffic scheduling. WiMAX is using OFDMA in the downlink and in the uplink. For the LTE, telecommunication, OFDMA is used for the downlink. By contrast, single carrier FDMA is used for the uplink since OFDMA contributes more to the PAPR related issues and results in nonlinear operation of amplifiers. IFDMA provides less power fluctuation and thus requires energy inefficient linear amplifiers. Similarly, MCCDMA is in the proposal for the IEEE 802.20 standard. These access schemes offer the same efficiencies as older technologies like CDMA. Apart from this, scalability and higher data rates can be achieved. The other important advantage of the above-mentioned access techniques is that they require less complexity for equalization at the receiver. This is an added advantage especially in the MIMO environments since the spatial multiplexing transmission of MIMO systems inherently require high complexity equalization at the receiver. In addition to improvements in these multiplexing systems, improved modulation techniques are being used. Whereas earlier standards largely used phase shift keying, more efficient systems such as 64QAM are being proposed for use with the 3GPP long-term evolution standards. Unlike 3G, which is based on two parallel infrastructures consisting of circuit-switched and packet-switched network nodes, 4G is based on packet switching only. This requires low-latency data transmission. As IPv4 addresses are, nearly, exhausted, IPv6 is essential to support the large number of wireless-enabled devices that communicate using IP. By increasing the number of IP addresses available, IPv6 removes the need for network address translation, NAT, a method of sharing a limited number of addresses among a larger group of devices, which has a number of problems and limitations. When using IPv6, some kind of NAT is still required for communication with legacy IPv4 devices that are not also IPv6 connected. As of June 2009, Verizon has posted specifications archived March 6, 2018, at the Wayback Machine that require any 4G devices on its network to support IPv6. The performance of radio communications depends on an antenna system, termed smart or intelligent antenna. Recently, multiple antenna technologies are emerging to achieve the goal of 4G systems such as high rate, high reliability, and long-range communications. In the early 1990s, to cater for the growing data rate needs of data communication, many transmission schemes were proposed. One technology, spatial multiplexing, gained importance for its bandwidth conservation and power efficiency. Spatial multiplexing involves deploying multiple antennas at the transmitter and at the receiver. Independent streams can then be transmitted simultaneously from all the antennas. This technology, called MIMO, as a branch of intelligent antenna, multiplies the base data rate by the smaller of the number of transmit antennas or the number of receive antennas. Apart from this, the reliability in transmitting high-speed data in the fading channel can be improved by using more antennas at the transmitter or at the receiver. This is called transmit or receive diversity. Both transmit/receive diversity and transmit spatial multiplexing are categorized into the space-time coding techniques, which does not necessarily require the channel knowledge at the transmitter. The other category is closed-loop multiple antenna technologies, which require channel knowledge at the transmitter. Open Wireless Architecture and Software-Defined Radio, SDR. One of the key technologies for 4G and beyond is called Open Wireless Architecture, OWA, supporting multiple wireless air interfaces in an open architecture platform. SDR is one form of Open Wireless Architecture, OWA. Since 4G is a collection of wireless standards, the final form of a 4G device will constitute various standards. This can be efficiently realized using SDR technology, which is categorized to the area of the radio convergence. 4G introduces a potential inconvenience for those who travel internationally or wish to switch carriers. In order to make and receive 4G voice calls, VoLTE, the subscriber handset must not only have a matching frequency band, and in some cases require unlocking, it must also have the matching enablement settings for the local carrier and/or country. While a phone purchased from a given carrier can be expected to work with that carrier, making 4G voice calls on another carrier's network, including international roaming, may be impossible without a software update specific to the local carrier and the phone model in question, which may or may not be available, although fallback to 2G/3G for voice calling may still be possible if a 2G/3G network is available with a matching frequency band. A major issue in 4G systems is to make the high bit rates available in a larger portion of the cell, especially to users in an exposed position in between several base stations. In current research, this issue is addressed by macrodiversity techniques, also known as group cooperative relay, and also by beam division multiple access, BDMA. Pervasive networks are an amorphous and at present entirely hypothetical concept where the user can be simultaneously connected to several wireless access technologies and can seamlessly move between them. See vertical handoff, IEEE 800 and 2.21. These access technologies can be Wi-Fi, UMTS, Edge, or any other future access technology. Included in this concept is also smart radio, also known as cognitive radio, technology to efficiently manage spectrum use and transmission power as well as the use of mesh routing protocols to create a pervasive network. Thank you for watching this video.